much. We're going to go ahead and get started with our next presenter. So thank you, Stephanie, for joining us. We're really excited. So Stephanie works at Lockheed Martin on commercial civil space. So I'll let you introduce yourself during your talk, though.
Awesome. Well, hi, everyone. Like you said, I'm Stephanie Shantz. I'm a mechanical engineer at Lockheed Martin Space in the Advanced Programs team. Today, I'll be going through Artemis to the moon and beyond. The agenda for today, I'm going to get started with a quick introduction, a little bit about myself, go into a brief overview of the Apollo program, how we've leveraged that science collection in those missions to catapult our pursuits into the 21st century with Artemis. And then I'm going to spend the majority of my time discussing the Artemis program with a review of Lockheed Martin's Orion spacecraft, and then touch on how Artemis enables sustainable deep space exploration. And if we've got time at the end, I've got a little bit of unsolicited advice of what I wish I knew when I was in college coming into the workforce. All right, so about me, Stephanie Shantz. I'm a mechanical engineer with Lockheed Martin Space Advanced Programs. Currently, I'm supporting commercial civil spaces technology development for the NASA NextSTEP Habitat program. So that's working on both lunar and Mars habitats. And I also do some internal research and development work on lunar surface architecture, different trait studies there. So I've got 2 years of experience at Lockheed Martin in various mechanical engineering roles. So I was just recently a crew systems engineer on our human landing program as a part of the national team proposal. So crew systems is everything that the crew touches, we were responsible for. So a lot of crew integration. I also worked a lot of requirements definition, and I was our lead for lunar dust mitigation efforts. So before that, my first position at Lockheed Martin was a mechanical design engineer for SBM in the electronics packaging team within the avionics organization. So had a lot of experience in the past 2 years, 3 different positions, experience in systems engineering, component design, and then some developmental testing. And then back in college, I had internships with General Atomics Aeronautical Systems and Leidos. And I am a proud Michigan alumni, graduated in 2019 with a BS in mechanical engineering. Outside of space and work, I am an avid hiker. I live out in Denver, Colorado, so it's basically the gateway to any exciting adventure you want to go on. So if I'm not at work, I'm definitely out on the trail. So today I'm going to get started with a video put together by our friends at NASA that really sets the stage for returning to the lunar surface.
Many people don't know is that Apollo had a twin.
She was a woman named Artemis, goddess of the moon.
We are returning to the moon
As a new generation of explorers, this time to stay
and to prepare to achieve humanity's next chapter of sending the first human missions to Mars.
We believe our course will redefine what is possible.
That we would discover life-saving,
Earth-changing science.
and that the challenges ahead will inspire generations.
This is our message.
For all who wonder if we could return,
From the dreams of something beyond.
this is your calling. We go for all of America.
We go. We go as the Artemis generation.
We go.
Awesome. So Artemis is the next step to returning to the lunar surface. The last time we were there was in 1972 with Apollo 17. And so Artemis will follow a similar flight structure as Apollo, starting out with Earth orbit for more basic systems checkout, then pushing beyond to lunar orbit before sending crew to the lunar surface. So we learned a lot from the Apollo missions, just even by where they touched down. So I'm going to go over a little bit of the different landing zones. So the Apollo missions landed in the Mare region of the moon, which is these dark basaltic plains on the moon that are formed by volcanic eruptions. So they're relatively flat, have some craters, but a very hospitable landing zone. And they also explored the lunar highlands region, which have a lot more intense cratering. And so overall, the Apollo missions really landed in mostly this equatorial region of the moon, which is a very, like I said, hospitable landing zone, had some logistic advantage of constant lighting conditions. And so to divulge from that, Artemis 2024 landing, which will put the first woman and the next man on the moon, aims at landing in the lunar South Pole, which is unexplored terrain, to hopefully explore water ice believed to be there in the dark craters where sunlight cannot reach. So Apollo proved that humans could travel to another place in our solar system and live and work, and Artemis is aimed at stepping beyond that and creating a sustainable presence on the moon. So now I'm going to go through a couple of my highlights and lessons learned from Apollo that I've seen kind of play into this technology development as we aim for lunar exploration. So Apollo 11, here I've highlighted the EVA activities. So EVA is extravehicular activity. And so that is when you're out and about on the lunar surface. So these EVA activities provided one, insane sample science collection opportunities, as well as opportunities for developing the suits and enhancing crew mobility on the surface. I'm sure everyone's seen the videos of astronauts tumbling around because they're so off kilter. And so there's been a lot of lessons learned from both data gathered and astronaut testimonials on how to actually improve that mobility and make it a lot easier to be mobile on the lunar surface. Then on the other side of the screen, I've got the Apollo 12 lunar descent. So studying lunar descent helps characterize plume impingement issues. So as you close in on the surface, your engine plume actually kicks up a lot of dust and debris. So we learned that we need to be able to, one, design the spacecraft to accommodate those debris strikes, as well as be able to have a field of view sufficient enough when that dust field kicks up that a manual piloted mission would still be able to land. So you want to be able to preserve that field of view so you can safely land on the lunar surface. So some Apollo 14, 15 lessons learned. Got an image of the Apollo 14 recovery here. So the ocean recoveries from the Apollo missions gave a lot of insight on, one, operations of safely retrieving astronauts and approaching a vehicle that has just fallen from space, as well as development in inflatable technology. So the Orion uprighter system is very similar to this inflatable system, but it's a lot more mass efficient. It doesn't utilize the full raft around the vehicle, and it helped gather information on different material properties of those inflatables and how to effectively deploy them. And then on the other side of the screen, we've got the lunar roving vehicle. So Apollo 15 was the first mission to deploy a lunar rover, which marked a turning point in lunar surface mobility. The ability to traverse terrain in such a short amount of time could really streamline science collection, made missions a lot more efficient, which is very valuable when you're on the suit and those different life support functions. The clock is always ticking. So to be able to really streamline that time is such a key aspect in having sustainable operations on the moon, to the point where, in the lunar architecture studies we've been doing, lunar surface mobility is a huge, huge aspect in creating kind of that sustainable network of habitats and creating a lunar economy. It all hinges on the idea of mobility. So this slide, Apollo 16, 17, I'm really going to focus on lunar dust, a topic that's very near and dear to my heart. It is one of the most significant risks from a technical standpoint when looking at landing and sustaining presence on the moon. So you can see this picture here of Eugene Cernan after his second EVA on Apollo 17. This is the always used picture in the lunar dust community, you can see his suit is just coated with dust, and that is because as the dust particles sit on the lunar surface, they're constantly being charged by the sun's solar rays. And so they have an incredible amount of static cling to them. They will adhere to pretty much any surface, whether it's a suit, whether it's solar panels, mechanisms. And so it's very dangerous to technology deployment. The particles have very sharp edges because there's not a lot of erosion factors on the moon. And so those very sharp particles work their way into everything and have a lot of destructive properties. So a lot of work and research has gone into figuring out ways to mitigate dust so it doesn't hinder astronaut mobility, as well as mitigating it so it doesn't get into the cabin. It has some pretty adverse effects on crew health. If you're breathing in, those sharp particles are not very good for you. And so working on mitigating that so it becomes less of a risk to crew health. So you can see also on the slide, a little shout out to Harrison Jack Schmidt. He was the first geologist to actually walk on the moon for Apollo 17. He had a tremendous amount of insight in experience with collecting the samples on the lunar surface, as well as analyzing them when they returned. I had the pleasure of working with Jack on some of the research I was doing, and just a wealth of knowledge, brings up so many different techniques, and it's also cool to talk to an astronaut. So all good stuff. So departing from the Apollo era, there's so many lessons learned that we can take moving forward and take that next step from Apollo to Artemis. So a little overview here. Lockheed Martin's development of Orion is part of a larger lunar campaign. So Orion is a deep space vehicle, and its first stop is the moon. So Artemis 1, which is actually coming up later this year, will be the first human spacecraft to orbit the moon in the 21st century. It's an uncrewed flight test that'll go around the moon to test some very key systems, as well as returning from the moon will also give some key data, which I'll touch on later. Artemis 2 is the first humans to orbit the moon in the 21st century, so that'll be a crewed mission going around the moon. And then Artemis 3, you can see at the end here, will bring the crew to the gateway and down to the lunar surface with the human lander to achieve that goal of boots on the ground by 2024. So in addition to this human-focused travel with the Artemis missions, there's also several continuous projects, which I'm sure we'll hear about in this fantastic event. But one that is very interesting is the Commercial Lunar Payload Services, this CLPS program, it's different robotic missions to deploy hardware to the lunar surface, as well as lunar cargo delivery. So those are both really key aspects in being able to build up infrastructure on the moon. The CLPS program offers just invaluable opportunities to study hardware in the environment that it will be deployed in. So that is something that is huge on different landing technologies. So to be able to bring it there, test its capabilities, bring it back refined from data is just totally invaluable. It's so hard to replicate the moon on Earth, so having those opportunities is great. And then the cargo delivery programs allows that, next step of being able to actually deliver hardware to the moon, things like habitats, rovers, without sending the crew with them, is very valuable as we try and build up a base camp on the moon. All right, so Orion, this is Lockheed Martin's deep space exploration vehicle designed for NASA and actually fabricated by Lockheed Martin. So why Orion? Orion was developed to withstand lunar and deep space travel, which entails a far more robust requirement set than just going to low Earth orbit like a satellite. And so you can see kind of the fast facts here. It's 24 times longer, 73% hotter, 7,700 miles per hour faster on reentry, and it's over 1,000 times farther. And so what it takes to achieve this is a whole host of technology suites. So one, life support systems, advanced environmental life support systems designed for long duration missions to keep the crew safe and healthy as they voyage to the moon and beyond. Radiation protection, not something you need to worry about in low Earth orbit, but something that's very, very important to protecting the crew and spacecraft systems as you travel out into deep space, as well as heat shields. So this is an area where Lockheed Martin has a lot of experience with the different Mars surface deployments on creating heat shields for those. So this heat shield needs to be designed to take the extreme temperatures of about 5,200 degrees Fahrenheit coming back from the moon at 24,700 miles per hour, while keeping the crew safe and comfortable and not on fire. Then the propulsion system, so the service module of Orion, has 33 engines for maneuvering, including its large main engine that's used to provide high power deep space maneuvers. And then there's deep space communication and navigation. This is a huge aspect. Where Orion is going, there are no GPS or communication satellites, so there's a very unique system designed to be able to communicate back home as they execute the mission. And then redundancy. So this is another huge factor. When coming home quickly isn't an option, having redundant systems will ensure the critical elements, the computers, the life support systems are all remaining operable in the event that something goes wrong. Having redundancy in those systems is something that Lockheed Martin really prides ourselves in and making sure that it's done right. So an overview of the actual spacecraft. So on the far end, we've got the service module. So this module of the vehicle provides the spacecraft with electricity, propulsion, and critical life support consumables like oxygen and water. And then the crew module here in the middle is where the astronauts live and work and pilot the vehicle. So it's got sleeping accommodations, food preparation, waste facilities. It's a little space hotel for the astronauts. And then we've got the launch abort system. So launch abort system provides both protection to the crew during launch with the fairing you see there, as well as emergency abort capability during launch by pulling the capsule away from the launch vehicle in the event of a failure there. It features 3 different motors, and I'll talk about those as I get into some of our real world testing that we've done with the system. All right, so a little bit of Apollo Orion comparison. So on the high level, Orion is sized for more crew members for a longer stay. So Orion supports 4 crew for about 84 days of crew consumables. Consumables include water, oxygen, food, things like that. Whereas Apollo was sized for 3 crew members and only 39 days. And then one of the key difference between the 2 vehicles is the power source. So Orion is solar array powered. It's not dependent on an internal power source, and it was able to recharge power systems as it travels, which really helped enable that deep space capability, whereas Apollo was fuel cell powered with about a 14-day maximum life. Another item as a crew systems engineer that's near and dear to my heart is at the bottom of performance is the habitable volume. It is insane how small these vehicles are. You got to appreciate the astronauts for going and exploring. And so Orion features more habitable volume per person, which it doesn't seem like a large amount, but every cubic foot counts when you're that tight with the crew members. Awesome. So a couple of Orion real world images from our Lockheed Martin development. So this is the Artemis 1 crew module undergoing different tests. You can see it doesn't have its full outer protective shell assembled yet, just so you can access these different testing ports. So this is the crew module in real life. Here we've got the Artemis 1 crew and service module stack. So this is going through its final checkout testing before it is delivered out to NASA. Here is some of our crew evaluation and testing. So as a crew systems engineer, I learned very quickly that it doesn't matter what I think as an engineer, it is what your stakeholders who will be interacting with the vehicle are their opinions. So a lot of different mock-ups and then real world systems are used to interface with the astronauts, get early and often feedback. That was something that was huge on HLS. We created a full-scale mock-up and was able to have the crew come in, give some feedback on different layouts, different arrangements, and to be able to actually touch things in in life. Instead of looking at a CAD screen and saying, oh, I think my hand would fit in here to grab that, it is so much different to be able to actually do it. And especially in this case, you can see the crew is suited, which is another layer of constraint. You've got a lot more reduced mobility when you're wearing suits. And so to be able to test those parameters as well and make sure, you know, a normal person can grab something, but also a suited crew member can handle it as well. So some crew evaluation testing there. Here's some of the work at NASA's Neutral Buoyancy Lab in Houston. So NVL is used for a couple different items. Here you can see the Orion capsule in the water. They use it to test different inflatables at deployment of the uprighter system after splashdown. And it is also used in different applications where you want to simulate a different gravity condition. So, the moon is at 1/6 gravity, which obviously is very difficult to replicate. You don't have a lot of time on the Vomit Comet, and you can't bring the whole vehicle with you. So the neutral buoyance offers a unique opportunity to have that different gravity conditions, especially with mobility. So a quick overview of Orion's path to deep space. So we've gone through a handful of different checkpoints already. We've got the PA1, which is the pad abort test, is the first in a series of flight demos to test one facet of the launch abort system. Then EST1 is the exploration flight test, which I'll talk on the next slide, to actually send the vehicle up and around Earth. And then we've got AA2, which is the ascent abort test, which covered the full capability of the launch abort system. And then later this year, 2021, we'll be sending an uncrewed Orion module out around the moon. And then following that, we'll do a crewed mission and then start sending folks out to the moon. So exploration flight test 1 did 2 orbits around the Earth, and it provided just an invaluable amount of performance data on the vehicle system operations. So we tested separation events, which was 17 different events. The heat shield was a major component that we gathered data on. We were able to understand that the heat shield material erodes by 20% during reentry, which was allowed us to feed that back into our analysis models. It was a very continuous feedback type of process to design, test, design, test. And so that really helped feed into the cycle. Also looking at our radiation protection system. So being able to have sensors on the vehicle and test the real life radiation levels that were being experienced in the vehicle to then cross compare with our analysis, make sure we're on point and make any adjustments if necessary. So the data gathered from this EFT1 test was used to influence design decisions down the line, validate our existing analysis models, and then also help drive some innovative new approaches to space system development and overall reduce the mission risk and cost for the Orion system. So this is the Ascent Abort 2 test back in 2019. So they said this tested the full capabilities of the launch abort system motors as well as the parachute landing. And so in the event of emergency, the abort motor produces about 400,000 pounds of thrust to actually pull and propel the crew module away from the launch vehicle. Then that altitude control motor has the maneuverability to then offset it from the trajectory of the launch vehicle. And then the jettison motor actually pulls the launch abort system away from the Orion module so the parachutes can deploy. So that's kind of the inner workings of the launch abort system. Hopefully we'll never have to use it, but it's good to know that it does work. So Artemis 1. So this is what's going to happen during the first flight. So after one Earth, Orion will fly through the Van Allen radiation belts, spend about 4 days outbound to the moon. It will fly about 400,000 miles beyond the moon, further than we did during Apollo, and then spend about 6 days in the vicinity of the moon before returning 4 days to Earth. And so we're really excited about this test flight. It will gather a lot of good data, especially going through the Van Allen radiation belts. Like I said, gathering that radiation information to then cross-compare is very, very important to the system development, as well as testing the different insertion maneuvers as you change orbits. So Artemis now, in January of this year, Artemis 1 capsule, both the crew module and the service module, was delivered to NASA for full flight test integration. And then also in about the end of April here, the SLS, which is the Space Launch System core, was delivered to KSC to then again be added into the full stack and get ready for launch. So everything is on track for a November 4th launch this year, and we're really excited to see it fly. So I'm going to now get into some of the sustainable deep space exploration, what technology we have and where we're really going with it. So the path to Mars leads past the moon. So development of technology solutions on the moon provides just unparalleled research opportunities to evolve technology based on environments that will be similar between the moon and Mars, and trying to understand those different environmental responses while we have the chance. And creating a long-term presence on and around the moon allows us to really create that jumping off point for deeper space exploration. And so overall, Mars mission simulations on the moon come in two forms, really. So we've got in orbit around the moon and then on the surface. So these technology demonstrations in both areas really help us prepare for what it will take to get to Mars and then, establish a presence there as well. So items like deep space aggregation, practicing those docking maneuvers in space is a very complex item. Be able to rehearse that, vet the technology is very helpful for creating both a lunar and Mars type gateway systems. And then Mars transit habitat. So being able to test year-long missions around the moon is a very indicative environment of what it will be like to travel to Mars. So having that opportunity to collect the test data and then again, really refine the systems before we send them out is great. Then orbit to surface operations. So figuring out the ops behind having that orbiting gateway, delivering crew supplies to the surface, retrieving them, and kind of those rendezvous operations is good practice and something we want to vet when we have the very strong communications abilities instead of just relying on the deep space communication items when you're out around Mars. And then commercial resupply and refueling. So space refueling is a very hot topic. And so being able to develop that technology to actually have the capability is a huge focus. And then on the surface, like I said, spacesuit advancements, we learned a lot from Apollo. There's still so much more to learn. And so being able to have that astronaut feedback after actually using and wearing the suits is very key to be able to have something that's a lot more wearable, a lot more long-term. So a lot of spacesuit advances. And then like I touched on earlier, mobile operations, living and working on the go is huge to be able to really, if we want to just create a full, Artemis base camp on the moon, being able to travel around quickly and, save those valuable resources is very important. Planetary protection. So this covers both establishing our planetary protection laws and making sure you're just not throwing trash on the moon. And it also relates to sample collection. So developing technology so we can have pristine sample curation, making sure that you're not contaminating samples with other samples once you have them packed, making sure that you can actually seal them up and overcome those lunar dust impacts is very important. And then the last thing is human robotic exploration. So the idea of having robots running around on the moon, setting up sample collection sites before you get there is again saving those really key consumable resources. And that's something we can practice and develop on the moon to then deploy on Mars. So overall, the current investments in both crew launch capabilities with Orion and Gateway development, as well as the human lander development. Not only enables the Artemis mission to the lunar surface, but also serves as a foundation for deep space exploration as we take the next step to Mars. The buildup of lunar infrastructure through, the Artemis base camp will allow scientific collection and resource utilization to flourish, helping, create and grow, a lunar economy. And the sustainable presence on the lunar surface also allows us to demonstrate and refine those technology solutions for applications to deep space and Mars mission execution. So that is all I have on Artemis and space. I'm getting pretty close to my time, so I'm going to just briefly go through what I wish I knew in college. So Stephanie's fast facts. Don't be just book smart. There are so many student organizations, design teams, opportunities to grow your experience and your knowledge outside of the classroom. So take advantage of that. I was on the Michigan Hyperloop team and grew so much engineering skill, just being able to be assigned a piece of hardware and design it and create it and not have it be a little RMP and ME250 is very, very fun. Another item is learn the value of networking and building connections. You never know what personal connection can help you flourish in your career. And so taking the time to get to know people and building your team will really help you as you grow into your career. Another one, I should have highlighted, bolded it. Communication skills and people skills are so important. You could be the most brilliant engineer ever, but if you cannot explain your ideas to someone else, they're never going to go anywhere. So I know as excruciating as it is for some engineers, take some time to hone those communication skills because it will absolutely pay off in the long run. And then the last one I have is you don't have to have your entire life figured out right now. I definitely don't. Just, next couple of steps, understand what you're interested in and what you want to do. You don't need to have, this is my 10-year plan and I'm going to change jobs every 2 years, but it's just have a couple steps figured out and know what you're interested in. And another thing is not every position is a permanent stop on your career trajectory. Like I said, I've had 3 jobs in 2 years, did not plan it that way, but it's all fantastic experience, and you're not married to a job once you get it. There's a lot of opportunities to grow and develop and hone different skill sets if that's what you're interested in. And then one last tip is an interview specific tip. Just remember, in any interview, everyone you're talking to is just a person. There's no need to be stressed. They're just a person like you. And they're interviewing you, but you're also interviewing them. So get to know them, ask them how their day's going. It'll really help relax the energy of an interview. And I found that it's very positive if you just treat everyone like a person. All right, so that is the end of my presentation. Do you guys have any questions?
Oh, thank you, Stephanie. That was awesome. It's good to be reminded of some of those things and then what I wish I knew, because I'm 4 years into it and I'm still like, it's okay. You can calm down. You don't have to overplan. But yeah, we do have time for a few questions. So if anybody wants to type into the chat, go right ahead. But to start off, oh,
we have a raised hand.
Oh, yes.
Okay, give us 1 second to find you.
I think it's at the top.
Okay.
Maybe. Yeah.
Oh, there we go.
Hey, Stephanie, how are you doing? It's Sama. I have a question for you. Can I ask?
Yeah, absolutely.
I wanted to ask what type of thrusters Orion spacecraft is going to use, and what rocket boosters Artemis system is gonna use.
So Artemis is going to utilize the SLS. So that is NASA's Space Launch System. They've been developing it, oh my God, forever. And so SLS is made up of a couple different stages. That image I showed was the main core stage. I'm not as familiar on it because it is a NASA developed technology, but they did just undergo their green light testing, so they are on par with also being ready to launch, and also getting all of their testing data set up so they're ready to go. And then I missed the first part of the question.
Sorry, I got mute. So my first question was which types of thruster Orion craft is going to use, and on the Artemis system, I wanted to also ask: is Artemis gonna use same thrusters which were used in Apollo 11 spacecraft?
Yeah, so Orion and I guess the Orion crew launch for the Artemis missions will take place using the NASA SLS system. As far as the lunar lander, I have no idea what SpaceX is planning. I'm not very familiar with their launch capabilities with their human landing system, which will actually be the lander that goes to the moon in 2024.
Yeah. We also have a couple of questions in the chat, so I'll go ahead and read those out. So the first one is from a high school SEDS chapter. They are asking, what are the biggest problems you have faced with figuring out the human modules you'll send on Artemis?
I think the biggest challenge that we have, at least I've personally faced and seen programmatically, is balancing mass versus launch capabilities. So you're always trying to cut mass because you only have a select suite of rockets that you can launch using. And so being able to balance every aspect of a design when it comes to mass. So from a crew standpoint, we always want the habitable volume to be bigger. It's always a challenge to make sure that the astronauts have enough room to be comfortable and have all of the systems in place, but also, you know, battling the mass challenges of both the launch vehicle and then your own propulsion system. So that is one of the very high level challenges that I've seen very prevalent throughout all of the space industry, is just making sure that you're streamlining mass as much as possible and taking any opportunity that you have.
Great. I think we have time for one more question. There's one in the chat. So the next question is, our plan to launch Artemis 1 is in November 2021. But what if there is an unexpected uncertainty and we fail to launch? What would be the next launch window?
I actually do not know what the next launch window is. I think it would probably be a couple months following, depending on also it's, you know, when we actually have favorable launch conditions, but it's also trying to analyze and identify what the issue that precluded the launch was. So going through and making sure that you save enough time for an effective failure investigation, depending on, you know, the severity of the issue that stopped the launch. So you want to balance making sure that you correct the system, address any issues that there are, and then also figuring out when the time period is favorable to actually launch.
Great. Thanks so much, Stephanie.